The massive propeller of a supertanker slices through the waves as it enters a deep water port. On the Cree, a gigantic crane slowly brings down a steel pipe protected by a rubber layer onto the vessel's deck. Hydraulic clamps ensure the flange joints of the oil pumping pipeline are firmly locked in place. An engineer in protective gear manually turns a large gear wheel of a butterfly valve. The needle on the analog pressure gauge jerks wildly, instantly reaching 15 bar. Thick, black, bubbling crude oil aggressively rushes through the transparent sight glass. The impeller of a massive centrifugal pump spins rapidly, siphoning oil from the ship's hold. The unceasing flow of crude oil is forced through an extensive network of galvanized steel pipes along the quayside. An ultrasonic sensor attached to the pipe lights up a bright red LED, meticulously measuring the enormous flow. The dark liquid cascades violently into a colossal cylindrical storage tank equipped with a floating roof. Inside, a submerged mixer rotates slowly, preventing the thick sludge from settling to the bottom of the tank. A technician carefully inserts a long glass sampling tube, extracting a measure of crude from the drain valve. Inside the lab, an electronic balance instantly displays the precise density metrics of the oil sample. A high-speed centrifuge spins furiously, physically separating water and impurities from the dark oil film. Crude oil is moved directly from the storage tank to the preheating piping system by a very large suction pump. The thick crude sticks through the internal baffles of a massive shell and tube heat exchanger. Api the initial heat. An infrared thermometer runs along the outer steel piping, its display set at precisely 120 degrees Celsius. The pneumatic control valve opens abruptly and automatically, forcibly injecting a strong stream of fresh water into the heated oil. Internal blades of a static mixer violently churn, the fluids grinding them into a tight emulsion of oil and water. This newly formed emulsion is precipitated into a huge, horizontally positioned cylindrical salter vessel. A fierce 20,000 minus volt electric current arcs across the electrodes of the vessel's internal grid. Under the intense electric field, microscopic droplets of salt water are forced to collide and coalesce into heavy droplets. Now heavy, the muddy brine sinks to the bottom and drains out through a large bleed valve. A highly sensitive conductivity meter confirms that the salt concentration in the crude has dropped to perfectly safe levels. Clean, desalted crude oil rises to the top of the vessel and emerges in the main pipe, leading to the furnace. At the base of the imposing furnace, industrial gas burners ignite, shooting out a violent 2-meter blue flame. Inside the inferno of the combustion chamber, the enormous spiral pipes that transport the crude glow a deep cherry red at 400 degrees. A shielded temperature sensor immersed directly in the boiling stream sends a critical signal to the control room. Crude oil is boiling away, decomposing into a chaotic, frothy semi-liquid and semi-gaseous state. This roaring, seething mixture enters the enormous base of the atmospheric distillation tower at terrifying speed. The scorching gas rises, forcing its way violently through the thousands of tiny holes in the perforated trays. Meanwhile, the heavier liquid fractions accumulate and cascade continuously over the raised metal rears of each tray. The use of stainless steel bubble caps ensures the efficient and absolute transfer of heat by violently agitating the rising gas within the accumulated liquid. At the top of the tower, the lighter LP gas escapes through a large overhead pipe to the cooling station. A colossal 10- homeboard cooling fans spins at maximum speed, blowing cold air over a dense array of condensing tubes. The cooled gas rapidly condenses into a crystal clear liquid that drips steadily into a high-pressure collection sphere. Just a few trays below, the volatile crude naphtha undergoes comptation and quickly flows outward through a lateral branch pipe, the yellow skein. An engineer cautiously opens a sampling valve, collecting a stream of pale yellow naphtha in a glass Mayer flask. In the intermediate trays, the temperature drops just enough for the kerosene to condense into a smooth, slightly viscous stream. The kerosene is passed through a thin film net membrane filter, a process that meticulously removes all microscopic particles suspended in the fluid. Down lower in the massive column, the heavy diesel fuel condenses and forcefully falls in a thick cascade through the collection nozzle. Boiling diesel fuel is relentlessly propelled through a high-capacity seawater cooling matrix by a robust vane pump. Down at the base of the tower lies the atmospheric residue, a tar-black, incredibly viscous substance that moves extremely slowly. With its powerful steel teeth, a gigantic gear pump grinds relentlessly, physically crushing and pushing this stubborn sludge forward. The sludge is fed into a second, more powerful furnace where violent flames superheat the pipework to 410 degrees Celsius. Yeah, buddy. In inline digital pressure sensor peaks, indicating the immense force propelling the fluid into the vacuum tower. The superheated residue is aggressively atomized through a multi-jet nozzle, spraying a dark mist into the tower's absolute vacuum. Above, a high-velocity steam jet screams continuously, forcibly sucking in gases to maintain the critical deep vacuum. At this near-zero pressure, the heavy sludge instantly bursts into vapor, preventing complete thermal destruction. The liberated molecules of vacuum gas oil, or VG, precipitate upward into intricate layers of geometrically structured packing, heat packing. As the hot gas violently strikes the cold corrugated metal surface, it instantly condenses into heavy droplets of heavy liquid. These blistering droplets of VG either fall continuously like rain, splashing into its specialized shaped recovery pans. A turbulent river of opaque VG pours profusely through a wide side discharge pipe in the tower's flank. In the darkest pit of the vacuum tower, the final, uncut residue of dense black asphalt slumps to the bottom. A massive steel scraper blade drags endlessly in a circle, preventing the molten asphalt from cooling and solidifying into rock. The liquid asphalt is forced through a specialized double-walled pipe jacketed with steam and wrapped in thick insulation. The high-speed robotic arm makes a rapid, dual, precise movement to apply a tracking barcode label onto the finished asphalt container. Returning to the VG, high-pressure pumps propel this valuable oil directly into the mighty fluidized catalytic cracking unit. A powerful atomizing nozzle completely disintegrates the thick VG stream or explodes it into an ultra-fine, highly combustible mist. Within the vertical pipe, this powerful mist collides violently with a fiery sandstorm composed of microscopically small zeolite catalyst dust. At 540 grams, the devastating contact physically breaks the long, heavy hydrocarbon chains into lighter, high-octane fragments. A shielded infrared camera mounted on the riser wall observes the terrifying ultra-high temperature reaction vortex. Spent catalyst dust, now coated in deep black carbon coke, falls violently into a massive centrifugal cyclone separator. Immense centrifugal forces mercilessly pummel the heavy, dirty catalyst particles against the outer steel wall, separating them from the valuable gas. The heavy contaminated catalyst plummets through a vertical tube into the infernal regenerator vessel, where it is met with a roaring blast of pure oxygen. The choking layer of coal coke instantly ignites, burning in a blindingly bright flash that superheats the catalyst to a red-hot state. Now purified and glowing white-hot, the glowing catalyst passes through a huge mechanical slide valve and is precisely metered back into the riser. Released from the catalyst, the valuable cracked product gas rises through a final stripping section to remove any stray particles. This roaring storm of cracked gas enters directly into the lower portion of the FCC unit's massive main fractionator tower. Thousands of bubbler bells and massive trays into dial FCC gasoline and light gases. A torrent of highly reactive raw FCC gasoline, also known also known as crack naphtha, flows forcefully past a heavy glass observation window. An advanced inline spectrometer instantly shoots a laser beam through the flowing liquid, continually analyzing its chemical composition. The control room's digital monitor urgently flashes a warning indicating a high sulfur content in this specific batch of raw cracked gasoline. Relentlessly, a robust piston drives this cold gasoline straight to the high-pressure other hydrotreatment unit for its crucial processing. A multi-stage centrifugal compressor located nearby emits a deafening scream as it compresses the pure hydrogen gas to a substantial pressure of 60 bar. This highly pressurized hydrogen is injected and violently mixed with the sour gasoline inside a convoluted static mixer pipe. The volatile mixture is forced through a massive heat exchanger where its temperature soars to 350 degrees Celsius. This scorching mixture falls encased in thick, tightly packed beds of cobalt and molybdenum catalyst pellets in the reactor vessel in Desalting. On contact, the tenacious sulfur molecules are brutally torn apart instantly, uniting with the hydrogen to form the deadly H2S gas. The roaring torrent of toxic liquid and gas shoots out of the reactor and straight through a huge, noisy, fan-cooled condenser inside the high-pressure separator vessel. Gravity and pressure forcing the chaotic mixture to split into separate liquid and gas. The refined sulfur-free sweet naphtha is channeled downward, gently flowing through a butterfly valve, which is just barely open at the bottom. Meanwhile, the deadly H2S gas rises to the top and is aggressively drawn into a recovery pipe painted a conspicuous warning yellow. A high-capacity absorber column features powerful nozzles that spray a dense mist of liquid amine solution in a downward direction. This torrential amine storm collides with the rising gas, chemically absorbing the H2S and turning it into a dark gray toxic liquid that rains down to the bottom. The desulfurized gasoline is pumped into the stripping tower to remove the light gases. Superheated steam blows upward from the bottom of the stripping tower. The vapor stream carries away light gases and residual hydrogen sulfide from the liquid gasoline. The processed heavy naphtha is introduced into an intermediate stainless steel storage tank. A diaphragm pump rhythmically forces the heavy naphtha into the catalytic reforming unit. The heavy naphtha stream passes through the fourth furnace, moving within red-hot radiant heater tubes at 500 degrees Celsius hot. The hot naphtha vapor enters a spherical reactor containing platinum catalyst beads. Straight hydrocarbon chains bend and form complex aromatic ring structures. The stream releases hydrogen atoms to form benzene and toluene. The high-octane reformate stream exits the reactor forcefully. The hot reformate flows through air-cooled thin tubes, condensing into a golden liquid. A centrifugal separator rotates to extract the generated hydrogen gas from the liquid reformate. Strongly, the hydrogen recycling compressor pushes the pure gas back to the main pipeline of the factory. The liquid reformate flows through a stabilizer tower to remove dissolved, liquefied petroleum gases. Water condensed at the bottom of the stabilizer tower is discharged through a steam trap, emitting a thick vapor. The fully stabilized reformate fills a tank designated for gasoline blend stock. Switching to light naphtha, a centrifugal pump powerfully propels the liquid into the isomerization unit. Aluminum chloride catalyst beads promote the complex bending of straight molecular chains. The isomerized dancing stream, with its new branched molecular structure, emerges boasting a much higher octane rating. A technician carefully checks the crystal clarity of the isomerized stream through a high-resistance sight glass. In the alkylation unit, the raw butane and isobutane gases are compressed into an ice-cold liquid at -5 degrees. A screw pump aggressively pushes this ice-cold liquid into a reactor containing concentrated sulfuric acid. The blades of a high-speed agitator violently chop the mixture, creating a thick, white, foamy emulsion. In this highly acidic environment, small molecules quickly coalesce to form large, high-octane alkylate molecules. The chaotic reaction mixture flows smoothly into a large capsule-shaped settling tank. The heavy, dark brown sulfuric acid quickly settles to the bottom and is pumped for continuous circulation. The stream of lightweight sulfur-free alkylate gracefully ascends to the top and overflows onto a special discharge chute. Newly formed liquid alkylate flows through a caustic washing tower, guaranteeing the complete neutralization of any residual acidity. Inside the neutralization tank, the mixture bubbles vigorously as the caustic solution attacks the acid. The pure high-octane alkylate flows smoothly into the refinery's main mixing piping network. In the central control room, the computer system displays dynamic graphs of the mixing ratio in real time. 4 automated ratio control valves, each located on a separate component line, open simultaneously and in perfect synchronization. A golden stream of reformate is aggressively sprayed through a mixing nozzle under immense pressure. The cracked naphtha stream is introduced on one side, instantly creating a strong vortex with the reformate. A completely clear stream of isomerate merges seamlessly into the vortex, dramatically reducing the overall density. Finally, pure alkylate is forcefully atomized in the center of the chamber to boost octane to its maximum. A high-precision metering pump dispenses a bright red antioxidant liquid directly into the freshly mixed gasoline. A micro-gear pump forcefully injects proprietary engine-cleaning additives into the fast-flowing mixture. An advanced optical color sensor visually checks the flowing liquid gasoline mixture for absolute homogeneity. Operating in a noisy fashion, an inline cooperative fuel research engine runs continuously, burning and testing incoming gasoline samples. As the engine's piston lever taps the computer, it carefully acoustic knocking. A bright green LED on the control panel illuminates, confirming that the final product meets the strict octane 95 standards. The massive stream of finished gasoline is forcefully forced through a turbine flow meter, rapidly spinning its internal blades. The finished gasoline is gracefully poured into a massive cylindrical storage tank with a capacity of 50,000 cubic meters. The storage tank's massive floating steel roof slowly rises, perfectly matching the rising level of gasoline. A high-precision radar-level gauge on the tank's roof emits invisible microwave beams to constantly scan the surface of the liquid. A small autonomous robot quickly walks the perimeter of the tank, actively searching for any leaks of hazardous volatile organic compounds. At the expansive loading gantry, a gleaming fleet of silver gasoline tankers lines up in an orderly fashion. A driver swipes a magnetic ID card through the reader of the terminal's automation system to initiate loading. Nimurali ID. A heavy cast aluminum loading arm extends automatically and lowers smoothly directly into the open manhole of the tanker. The overfill sensor touches the floor of the compartment and emits a high-pitched beeping confirmation. Heavy-duty pneumatic clamps exert significant pressure, closing tightly around the tank's edge to guarantee a completely watertight seal. The copper ground wire drops down and clamps to the trailer, giving off a small, static spark before fading. A high-capacity centrifugal pump roars loudly as it forces gasoline from the center tank to the loading island tube. The digital meter advances rapidly, accurately counting each liter of gasoline entering the truck compartment. The automation display shows the flow curve climbing from 0 to 2,000 liters per minute. The toxic gasoline fumes ascending from the tank are drawn cleanly and efficiently into the recovery unit. At the recovery station, activated carbon absorbs the vapors and effortlessly returns the clean air to the environment. A powerful vacuum pump extracts the vapors from the carbon bed to convert them back into liquid. When the first compartment reaches full capacity, a solenoid valve instantly closes, cutting off the flow. The automatic loading arm gently lifts, dropping the last drops of gasoline into a dedicated funnel. The robotic arm firmly secures a lead safety seal onto the tank lid of the tanker truck. In a rapid operation, the inkjet printhead quickly stamps both the date and the barcode onto the freshly printed label. The massive loading arm moves to the second compartment to repeat the exact same filling process. Meanwhile, in a different area, the steel impeller of a massive pipeline pump spins furiously. A 5,000 minus horsepower electric motor generates immense thrust to send gasoline through the 500 minus kilometer pipeline. A differential pressure gauge blinks constantly, checking for any microscopic leaks along the entire length of the underground pipe. In the pristine laboratory, an engineer adds 3 drops of a special chemical to a sample of gasoline. A strip of pure copper is dipped into the test tube of gasoline and placed in a heating bath. After the waiting time, the copper strip retains its bright golden color, proving that the gasoline is non-corrosive. The satisfied engineer records the perfect data in an electronic logbook using a digital pen. High above the storage tanks, a relief valve releases a burst of protective nitrogen. A fire pump performs its weekly test, shooting a 15-meter column of water into the sky. An inspection drone equipped with a thermal camera circles the enormous gaseous flare tower. The giant flame at the top of the flare burns brightly, safely burning off any excess hydrocarbon gas. A huge LED board outside the refinery proudly displays a record 100 days without accidents. Convoy of dozens of loaded tanker trucks roars loudly, sending puffs of smoke from their exhausts. The heavy wheels of the first truck pass through a disinfection